Hello, I am Tigran Ishkanyan from Calculus and Algebra Group at Wolfram. So today I will talk about mathematical functions, new developments, and function properties. So here is the abstract that was available in the Pathable. And I will directly turn to the overview of the talk. So first, I'm going to talk about new features in mathematical functions. Then I will turn to Holdomic Functions, talk about what we have done for 12.2 upcoming, and at the end I will finish my presentation with some examples of analysis, function analysis, with a new functionality that will be in 12.2. Okay, so here is a slide with recent progress in the area of mathematical functions. So we are, of course, constantly improving all the available functionality, as well as developing and implementing some new mathematical functions. Just a couple of notes. So we have updated significantly the documentation pages, the basic example section and scope example section in 12.0 and 12.1. And you can just go to the mathematical functions guide or special functions guide and check different new examples in the documentation pages. Also, starting from 11.3, we are developing a very powerful asymptotic functionality. Also, we have implemented 5 new Hoyne functions with their derivatives in version 12.1. And for 12.2, we have improved dsolve. Now it's solving a lot of new examples, added, implemented 2 new elliptic functions, and also implemented the family of Laminar functions that are special functions. So I will here give a just brief overview on mathematical functions and on the philosophy that we are using. So key idea here is that most of the mathematical functions, elementary functions, special functions, are solutions of ordinary differential equations. And in fact, these differential equations can be used as data structures. So if we are working with the differential equations, then we have a lot of additional information that we can use. For example, we all know that the exponential function is solving this simple differential equation. The Bessel functions that are very popular and famous are solving a more difficult equation with singular points. And probably the most famous function, special function, mathematical function, is the hypergeometric 2f1 function that is solving a differential equation with 3 regular singular points. So hypergeometric functions generalize all the simpler mathematical functions. And in fact, hypergeometric functions played a crucial role in the development of science during the 20th century. But of course, there are more advanced, more complex special functions. So the spheroidal functions are examples. They are solving this equation. In 12.1, we made a big step in this field, implemented the family of Hoyne functions. The main function of this family is the general Hoyne function, and there are also 4 confluent forms of it. So the general Hoyne function is solving this equation. And the important point is that Hoyne functions directly generalize all the hypergeometric class of functions, all the functions from hypergeometric class, like Hoyne G, that is the general Hoyne function, generalizes the hypergeometric 2f1 function, and Hoyne C, that is the single confluent Hoyne function, generalizes the hypergeometric 1f1 function. However, if you will check the list of special functions, there was a family of special functions that was missing in Wolfram language. And this was the family of Laminar functions. And as we don't have them in Wolfram language, then we weren't able to solve the Laminar equation till the version 12.2. So the Laminar equation is this equation. And in the upcoming version of Wolfram language, we will be able to solve it. And so if you are in general interested in this topic, then you can just check my blog post that is, I think that is well written and rather detailed. However, as we don't have a lot of time, I will skip this and directly go to the new features in 12.2. So, as I've mentioned, we have implemented Laminar functions. There are two functions, Laminar and Laminar functions, also their primes, and two eigenvalue functions, because in fact, in the literature, the Laminar equation, we are solving eigenvalue problem. So this is a new step in the theory of special functions, because Laminar functions are implemented only in Wolfram language, so this will be something new. Matteo functions are their limit cases. In fact, Laminar functions are members of Hoyne functions family that we have recently implemented, but their importance is that Laminar equation and Laminar functions solve different problems, big set of problems from mathematical physics and quantum mechanics. And because of this, we have implemented these functions. So I think that these functions will be rather useful, and also implementing them in 12.2, we will activate the research in this area. As we have already seen that when we have implemented Hoyne functions in 12.1, researchers started using them, and in general, the field is activated. As we don't have a lot of time, I will just give a general overview. So Laminar equation is the following equation. Two Laminar functions are implemented, Laminar C and Laminar S. This equation is solved in terms of Laminar C or Laminar S only if this parameter h is specified to Laminar eigenvalue A or Laminar eigenvalue B. And here is the example of solving this equation. Here are some plots of these functions. Interestingly, these Laminar functions include sine and cosine functions as special cases when the elliptic parameter in Laminar functions, the last parameter, is 0. And this is very easy to understand because the Laminar equation is written here. And if this parameter is 0, then this is just an equation for sine and cosine functions. Now I will give some plots of Laminar functions. So this is a plot, the 3D plot of Laminar C. Here will be the plot of Laminar S for different values of elliptic parameter. These functions are doubly periodic. I will plot them. And this periodicity, the period depends on the order J, the second parameter of Laminar functions. Some words about the eigenvalues and derivatives. So we were forced to implement the derivatives, Laminar C prime and Laminar S prime, because the derivatives of Laminar functions are not functions of the same class. And because of this, we have implemented them, and their usage is, in fact, only while calculating the derivatives of Laminar functions. So here is the third derivative of Laminar S, and here we see Laminar S prime. About the eigenvalues, not a lot to say. Here is the plot, and here I'm showing that this Laminar equation is solved, only this parameter is specified to Laminar eigenvalue A. An interesting feature of Laminar functions is that there is a connection between Laminar functions and Hoyne functions. In fact, Laminar functions are proportional to Hoyne functions with specified parameters. And this is because the Laminar equation in its algebraic form, here it is nothing more than a general Hoyne equation. And we see that if this h is arbitrary, then the equation is solved in Hoyne functions. Now let's turn to the next two new functions, two new elliptic functions. So one function is called Jacobi epsilon. It's an important elliptic integral related to Jacobi dn. So here is the definition. And it can be used to calculate derivatives of Jacobi functions with respect to an elliptic parameter. Here it is. Other applications might be found in the application parts of documentation page of this function. The second function is Jacobi Zn. So here is the definition. And we see that it's closely related to Jacobi epsilon function. And here is a very presentable example how we can use this function. So this is a zero energy solution for the following periodic potential for the supersymmetric analog of this periodic potential. And by direct substitution, we can verify this result. So here it is. For extended discussion of this topic of Jacobi elliptic functions, integrals, and so on, check the guide page because it contains a lot of interesting examples. Okay, next improvement is connected with the Holdomic functions. So the key idea here is that we are giving a possibility to user to define its own special function or sequence, giving just the differential equation initial values or the difference equation and initial values. So if the user is interested in some function that is not implemented in Wolfram language, then a user can define its own function and work with it. Also take a look on this nice new typesetting that is also implemented for and prepared for 12.2. So here is the old typesetting and here is the new typesetting. It's nice and I truly like it. So else we have significantly improved the documentation pages for the differential root and difference root functions. We have implemented a new method of differential root calculations. And here we are using a series-based analytic continuation procedure. We have a better performance and a lot of interesting features like parametric derivatives of difference root and also a new typesetting that I've already mentioned. Here I will give just a brief functionality, how we can work with these differential root and difference root functions. So for example, if you are solving some equation that is unsolved in non-mathematical functions, then the output will be a differential root object. But however, you can use it just any other mathematical function in Wolfram language. For example, you can calculate some values, you can plot this solution, you can calculate the derivative of it, you can make some asymptotic analysis. This is very cool. Also, you can use a function called differential root reduce to, for example, generate the differential equation that is obeyed by Bessel functions, for example. Here you can use a combination of different functions. In any case, you will receive the differential equation and the initial and corresponding initial values. About difference root, so you can define your own sequence, calculate some, say, 10th term of it. You can generate a function which Taylor expansion is this above given difference root object. And of course, you can verify the result, calculating back the series nth coefficient. This is pre-calculated because it will take some time. Also, you can use difference root reduce now to calculate, for example, the difference equation that is obeyed by Bessel functions, Bessel sequence. Interesting point is that you can also have some parametric sequences, work with them absolutely like in the same way, like another mathematical function or sequence. Okay, so this was about holonomic functions. And now I will turn to the last part of my presentation that is on function properties. So this is an important improvement for the analysis of function properties. It will be available in 12.2. There are three general sets of functions that are analyzing the theoretical properties of functions, some analytic properties, and functions like this. So I think that everything is more or less understandable here. And I will show some examples how I'm using this functionality for analysis. Okay, so here I took the very simple cosine function. And I am very interested if this function is continuous, is injective, surjective, or bijective. So here will be the output. And of course, plotting this function, we can verify the result. Also, using these function properties, you can get the conditions when the function is continuous, monotonic, analytic, and something like this. So for example, let's take a rather complex function like this, difficult function like this, and generate the conditions when it's continuous. So it's continuous when these conditions are satisfied. Another example, let's take a function like this and get the monotonic and get the conditions when it's monotonic. So here it is. Of course, you can use the function analytic function to check if this function is analytic. This one is analytic, this one is not. And of course, you can use the plot 3D functionality to verify the result. So here we truly see that the first function is analytic, the second one is not analytic. Of course, you can work on a complex domain. For example, here I'm checking if this function is continuous on complex domain, and also using the powerful complex plot 3D function to verify the result. So we truly see that it's not continuous, and here is the plot of it. We see that there are two singular points. And you can use this functionality to generate the set of singular points. For example, I took the gamma function and then generating the singular points list. So here it is. You can, of course, use this functionality to get the discontinuities. For example, I took the Bessel function for some parameter, and here is the discontinuity. And of course, I can verify the result using complex plot 3D function. So here it is, and this is the origin, and we see that there is a discontinuity going to -infinity on a real axis. And the last example for today is the case of hypergeometric function. So I'm just taking hypergeometric 2f1 function, plotting it. We know that there is a singularity at 1. And just checking that function singularities is giving the correct output. And of course, I can also generate more general conditions on a complex domain. So here it is. I will repeat that this is in my opinion, this is a very important improvement and will be very useful for both students, researchers, and other individuals from the industry. So in fact, this is all for today. And I'd like to thank you for your attention, and I'm ready to answer some questions if there are. Okay. Hello.
Hello, can you hear me?
Yes, I can hear you.
Yeah, hello. My name is Galina Filipuk. I would like to ask actually a couple of questions to you.
Okay.
So first of all equations that you mentioned at the very beginning, the Hoyne equation, hypergeometric equation, and so on, as a derivative of the Hoyne equation, are examples of in general, of function equations with certain singular points. Well, I mean, and of course, and there are confident cases. Do you plan to implement just the general linear equation and try to classify it, or something like this?
In fact, the holonomic differential root is doing it.
But do you take into account all special values of the parameters that might happen? For instance, at some special values of the parameters, the parent singularity might appear, and for instance, the Hoyne equation, the derivative of the Hoyne equation, I mean, the linear equation might reduce to the Hoyne equation itself, if you see what I mean.
For the Horn case, this is done manually, I think, but I don't think that we'll do it for the general case.
Did you implement any kind of quadratic and in general, say, cubic transformations between, say, hypergeometric functions or between Horn and hypergeometric functions, again, which happen for special values of the parameters?
Yes, there are some examples that I have implemented. Not all the examples that can be found in the literature, but most important ones are implemented for sure.
Yeah, and what about, so you spoke about some asymptotic expansions. Did you implement also expansions containing, say, logs?
Logs?
Yeah.
Logarithmic functions. No. The problem with Horn functions is that they are very general, and the theory for them is not complete. So because of this, there are different articles, but most of the articles are tackling some specific problems, not general problems. And because of this, there is some trade-off, what to implement and what not to implement.
I see. And the last question, so you spoke about, in general, about singularities, but sometimes, say, if we are looking at the linear equations, some singularities might be apparent.
Yes, yes.
Do you classify somehow, well, I mean, do you eliminate such kind of cases, or this is you take some, again, generic values of the parameters?
No, we are taking only the general values.
Okay, thank you.
Thank you for your questions. I see that Oleg is here, and hello, Oleg. I have unmuted you. Yeah.
Okay. How about function branch cut? I don't see this characteristic in list of new characteristics.
Discontinuities or branch cuts?
No, logarithm from Z, branch cut from -infinity to 0. To show line where we have branch cuts.
For which functions?
For arcsine, for example, for logarithm, for compositions of this.
Yeah, I think that you can go to the documentation page and take examples from there.
The function side has this characteristic.
Yeah, also the function side, of course.
Yeah. Why not implement it yet? Forgotten.
I don't know. So I think that Adam can answer this question.
And also, it's nice to have a special plotting for branch cuts to show where we have branch cuts for each function.
Before my talk, there was a talk on complex visualization, and they were showing very different and very powerful plotting techniques. So more or less this is done, I think. Not for the old functions, of course, but for the elementary ones, everything is done, I think.
Okay.
Okay, so are there some other questions? Well, I've checked this pathable. It seems that there are no additional questions. Nice talk. Yeah, thank you, Devendra. Thank you, John. Then, if there are no questions, I think that we can stop here.
Actually, may I have one more question?
Yes, of course.
Do you plan to go into some nonlinear special functions?
Yes, it will be done in future.
What particular do you plan to implement?
The next chapter in the digital library of mathematical functions.
So which one is that?
Penlever functions.
So what particular functionality do you plan to implement there?
I cannot say because this is a very, very future thing, but of course there are plans to implement also nonlinear sum equations functions.
Okay, thank you.
Okay. There is a question Yes, I think that FoxH. So the question is about will the FoxH function be implementing? Are we working on this? Yes, probably it will be. We will start actively working on this after this release, upcoming release. And thank you for a question. Okay, I will wait maybe one more minute for some questions, maybe.
And how do you plan to work with movable singularities in nonlinear equations?
I cannot answer this question at the moment.
Okay, thank you.
But I know that you are actively working on the topic, so probably I will ask some questions.
Yeah, sure, thank you.
Mm-hmm.
So can I say something?
Yes, of course.
Okay, Fox should come with its important cases. We have only one case, Mittag-Leffler, but other cases like right functions should be their analogous of hypergeometric PFQ function. And of course, interesting question. You converted these differential roots into series.
Mm-hmm.
And in many situations, such series can be recognized as expansions of already existing functions, like basic functions.
Right.
So, and you will be able to restore and convert this root differential into Bessel and other known functions for us. You can go also through Meyer G in this procedure.
Mm-hmm.
Are you doing this or plan to do?
I think that we'll start working on this. Okay. I think that time is more or less over. So once more, thank you everyone for your time, and goodbye.
Goodbye. Very interesting talk.
Yes, thank you. Goodbye.